If you were to take a balloon and blow it up and then release it, you'd expect to see the balloon fly around the room in a seemingly chaotic manner and eventually drop to the floor. It's the momentum of the air leaving the balloon that provides the force causing the balloon to move. We see the same effect when a rocket pushes some of its propellant out through its nozzle, although hopefully the rocket's motion is a little more under control. In this video, we're going to see how we can calculate the force on an object when we eject some mass from that object with some velocity. We'll rely here on the concept of conservation of momentum, a principle that comes directly from Newton's second law: force is equal to mass times acceleration, or F is equal to ma. The concept of conservation of linear momentum can be stated as linear momentum remains constant when no external forces act on a system. Now, the linear momentum is defined as linear momentum is the product of mass and velocity, with velocity being a vector. So here m is equal to the mass and v is our velocity. So let's consider an object. So say we have an object and that object has some mass m. Let's say it's got some velocity v, and we'll consider it at time t. So consider time t. We've got this object with some mass and some velocity. Let's now move on to a slightly later time, time t plus delta t, where delta t is a very small increment in time. Then, during this increment in time, let's assume that a small amount of the mass of this object is ejected from the object. And let's say that its mass is going to be delta mp, and let's say its velocity is going to be v plus v subscript p, where vp is the velocity of that small mass relative to the large mass. So let's just write that down, important point, where v subscript p is going to be the velocity of our small mass, delta mp, relative to, and that's the important point, relative to the mass m. So at this time t plus delta t, our mass is now m minus delta mp, and our velocity has changed, and our velocity is v plus delta v. So that's the velocity of the large mass that's left. Now there are a few important assumptions that we're going to make. The first is that delta t is very small time step, is a very small time step. We're also going to say that delta v is small compared with or relative to v. So the change in velocity of the large piece of mass is relatively small. Also our delta mp, so the amount of mass that we're pushing out, is small relative to the overall mass, or the initial mass of the system, m. So let's just move our page down. And let's now go on and conserve our momentum. Over that short time step from t to t plus delta t. So conserving momentum is going to give us that the initial momentum is mv, mass m, velocity v. At our slightly later time step, our mass is now m minus delta mp, and that main mass is moving with velocity v plus delta v. But we've also got our mass that we've ejected, so that's going to be delta mp, and it's going to be moving at v plus its relative velocity vp. So let's just expand that out a little bit. So our left hand side stays as mv. The right hand side we're going to get an mv. We're going to get a m delta v minus a delta mpv minus a delta mp delta v plus a delta mpv and a delta mpvp. So we have quite a few terms there. There's a couple of terms that we can get rid of. First of all, we've got a minus mp delta mpv and a plus delta mpv, so they cancel out. The other term that we're going to look at is this term here. So we get this minus delta mp delta v. Now we said that delta mp is small relative to m and delta v is small relative to v. So this term here is small compared with all the other terms, so we can neglect it. So let's neglect this as small relative to the remaining terms. And slide our page down. What we end up with is we get that m delta v plus delta mp vp is equal to 0. And in order to get that, I've also noted that there's an mv on each side of that equation. So that's what we're left with coming out of those expressions. Let's now write this. So let the mass be emitted continuously during this short period of time, and let's divide each side of our expression by delta t. And let's also, during this period of time, let's assume that Vp, as this mass is ejected continuously over this period of time, is constant. Let's write that again. Alright, just erase that. So Vp is constant. Then what we end up with is we get m delta v over delta t plus delta mp over delta t times vp is equal to 0. Let's now take a limit on this and let's let delta t, which is very small, let it approach 0. And if we do that, then our delta v over delta t term in the limit as delta t approaches 0 becomes the derivative dv dt, and similarly delta mp over delta t becomes dmp dt. So that will give us m dv dt plus dmp dt times vp is equal to 0. Let's just move the screen down again, and let's rearrange this now. And write it as minus dmp dt times vp is equal to m dv dt. And let's just make a couple of points. Let's note that the rate of change of velocity with respect to time is just the acceleration. By definition, the acceleration is the rate of change of velocity with respect to time. So this term here is our acceleration. So the right-hand side is just ma. And so what we have there is that this ma is an effective force. So therefore we can finally write that the effective force due to ejection of mass we'll call that F is equal to minus dmp dt times the velocity with which we're ejecting that mass. And so that's the expression that we've been looking for. So let's just have a look at that. The first important point to note is that the effective force on an object is in the opposite direction to the direction in which we're ejecting the mass. So if a rocket was to expel mass from a nozzle at its base, it would accelerate in the opposite direction, and that's what we see. It also shows us that to get a higher force, we should push the mass out at a higher speed, so have a higher value of Vp. The force increases linearly with the speed that we eject the mass at. Then it shows us also that we can increase the force by increasing the rate at which we eject the mass, so a higher dmp dt. Again, this is a linear relationship, so if we double the mass flow rate, dmp dt, we double the effective force. We'll see how we can use this for a rocket in the next video.